In this video, we will discuss curve sketching, which can be considered as the central topic of differential calculus. And indeed, as you could see, so far we have been concerned with some particular aspects of curve sketching. In chapter 1, we studied domain, range, and symmetry of a function. In chapter 2, we studied the limits, continuities, and asymptotes. In chapter 3, we studied the derivatives and tangents. In chapter 4, we studied the extreme values, intervals of increase and decrease, concavity, points of inflection. Now is the time to put all this information together to sketch graphs that reveal important features of functions. Before going into more details, let's first answer the following question. Why don't we just use a graphing calculator or computer to graph a curve? Why do we need to use calculus? Well, it's true that modern technology can produce very accurate graphs, but even the best graphing devices must be used intelligently. So it is easy to arrive at a misleading graph or to miss important details of a curve when relying solely on technology. Okay, for instance, the following figure 1 shows the graph of this polynomial function 8 times x cubed minus 21 times x squared plus 18 times x plus 2. So this is the graph of this polynomial function. So at the first glance, it seems reasonable. It has the same shape as cubic curves like y equals to x cubed, and it appears to have no maximum or minimum point. But if you compute the derivative, you will see that there is a maximum when x equals to 0.75 and a minimum when x equals to 1. Well, this information is not clearly seen on this graph, but if you zoom in, you will find that the function has got a local minimum when x equals to 1 and has got a local maximum when x equals to 0.05. So without calculus, we simply look at this picture. It's very easy for us to overlook such detailed features. Okay, so this is an example explaining why we need calculus for graph sketching. Let's go over the guideline of sketching the curve. So the first step is to determine the domain. It's often useful to start by determining the domain D of f, that is the set of values of x for which f of x is defined. The second step is to determine the intercepts. The y-intercept is simply f of 0, and this tells us where the curve intersects the y-axis. To find the x-intercepts, we set y equals to 0 and solve for x. So, but this step is not always necessary. You can omit this step if the equation is too difficult to solve. The third step is to investigate if there exist symmetries on the graph of the functions. And there are 3 types of symmetries we should investigate. The first type of symmetry happens when f of x minus x equals to f of x for every x in the domain. If this happens, then f is an even function, and the curve is symmetric about the y-axis. So this in particular means if you know what the curve looks like for x positive, then we only need to reflect about the y-axis to obtain the complete curve. So this is a graph of an even function. And to draw the graph, all we need to do is to first figure out what happens when x is positive and draw this part. Then we just reflect this part about the y-axis to obtain the complete curve. So this is one case when the symmetry simplifies the process of graph sketching. Okay, the second case happens when f of minus x equals to negative of f of x for every x in the domain. If this happens, then f is an odd function and the curve is symmetric about the origin. Again, we can obtain the complete curve if we know what it looks like for x positive. So all we need to do is to rotate 180 degrees about the origin. So here is the graph of an odd function. So once we figured out how the graph looks like for x positive, all we need to do is to rotate this graph 180 degrees to obtain this part. So this is another case where the symmetry helps to simplify the graph sketching. Okay, so the third case happens when f of x plus p equals to f of x for all x in the domain D. So here p is a positive constant. If this happens, then f is called a periodic function, and the smallest such number p is called the period. So for example, the function y equals to sine of x has period 2 pi, and the function y equals to tangent of x has period pi. So if we know what the graph looks like in an interval of length p, then we can use translations to sketch the entire graph. This is the graph of a periodic function. To sketch the graph, all we need to figure out is what happens within a period. So namely, if we figured out what happens between a and a plus p, so we draw this part of the curve, then to complete the graph, all we need to do is to translate this part of the graph to the left and to the right by p units, 2p units, etc. So this is the third case when symmetry helps in simplifying the process of graph sketching. Okay, so these are the three types of symmetries we should investigate for all the functions we want to sketch. The next step is to determine the asymptotes. The first type of asymptote we should investigate is the horizontal asymptotes. Recall from section 2.6 that if either the limit of f of x at positive infinity or at negative infinity equals to L, if either of these two cases happens, then the line y equals to L is a horizontal asymptote of the curve y equals to f of x. If it turns out that the limit at positive infinity is plus minus infinity, then we do not have an asymptote to the right. Or if the limit at negative infinity is positive or minus infinity, then we do not have an asymptote to the left. Still, this fact is useful for sketching the curve. So this is to say we should always investigate the limit of f of x when x approaches positive infinity and when x approaches negative infinity. So this is the first type of asymptotes we should investigate. The second type of asymptotes we should investigate is the vertical asymptotes. Recall the definition. The line x equals to a is a vertical asymptote if at least one of the following holds. Well, if the right-hand limit of f at the point a equals to infinity, or the left-hand limit is infinity, or the right-hand limit is minus infinity, or the left-hand limit is minus infinity. So to decide the vertical asymptotes, you need to locate the values of a where one of these four cases happens. So for rational functions, this is pretty easy. You can simply locate the vertical asymptotes by equating the denominator to 0 after canceling common factors. But for other functions, this method does not apply, and you need to investigate carefully using the properties of those functions. Okay, another remark is that it's very useful to know exactly which one is true. So this information will help us to determine how the graph looks like. Another remark is if f of a is not defined, but a is an endpoint of the domain of f, then it is always helpful to compute those one-sided limits and see if the limit is infinite. So many vertical asymptotes happens at the endpoint. Okay, so the third type of asymptote is called the slant asymptotes. This is not required in this course, but if you're interested, example 6 in the textbook discusses such an example. So please read this part by yourself if you're interested. All right, so this is the fourth step. We need to determine if we have horizontal asymptotes, vertical asymptotes. Now, the fifth step is to determine the intervals of increase or decrease. To do this, we will use the increasing-decreasing test. We need to compute f prime of x and find the intervals on which f prime of x is positive, which means f is increasing. And we also need to find the intervals on which f prime of x is negative. Well, this will mean that f is decreasing. The next step is to find the local maximum and minimum values. To do this, you need to find the critical numbers. Well, recall the definition. A number c is a critical number if f prime of c equals to 0 or f prime of c does not exist. Then you should use the first derivative test, and let's recall what this test says. If f prime changes from positive to negative at c, then f of c is a local maximum. If f prime changes from negative to positive at c, then f of c is a local minimum. you need to use the first derivative test to tell if f of c is local maximum or f of c is local minimum, or, well, there might be other cases like f of c is simply the point where the tangent is horizontal. So it's neither local max nor local min. Okay, so although it is usually preferable to use the first derivative test, you could also use the second derivative test if f prime of c equals to 0 and f double prime of c is non-zero. The second derivative test will tell you that f double prime of c is positive, which means f of c is a local minimum, and f double prime of c is negative, implies that f of c is a local maximum. So this is how you locate the local maximum and minimum values. All right, so step 7, you need to determine the concavity and points of inflection. So to do this, you will have to compute f double prime of x and use the concavity test. The curve is concave upward, where f double prime is positive, and concave downward, where f double prime is negative. Inflection points occur where the direction of concavity changes. With all the information you have obtained in these 7 steps, you will be ready to sketch the curve. Well, we always start by sketching the asymptotes as dashed lines, and we plot the intercepts, maximum and minimum points, and inflection points. Then we make the curve passing through these points, rising and falling according to the intervals of increase and decrease, with concavities according to our analysis of concavity and points of inflection. And finally, they should be approaching the asymptotes. So these are the steps you should follow in sketching a curve. As you can see, well, we are basically using everything we have learned so far. In step A, B, and C, we have learned that in chapter 1, and step D, we have learned in 2.6. And in step E, F, and G, we need to use our computational techniques obtained in chapter 3 to obtain the first derivative and the second derivative. Then we need to use the knowledge we have learned in chapter 4 to analyze the intervals of increase or decrease, local maximum and minimum values, and analyze the concavity and points of inflection. Then we will be ready to sketch the curve. So this is why curve sketching is the central topic for differential calculus. All right, so let's carry out these steps for the following example. We use the guideline to sketch the curve y equals to 2x squared divided by x squared minus 1. So this is a rational function. Let's start by deciding its domain. So this function is defined whenever the denominator is non-zero. So the denominator is non-zero means x plus 1 times x minus 1 is non-zero. So this in particular implies that x should not be equals to minus 1 and x should not be equals to 1. Okay, so this way we decided the domain to be minus infinity to minus 1 union minus 1 to 1 union 1 to infinity. All right, so this is the domain we have obtained. Now let's decide the intercepts. So we first set x equals to 0 to obtain the y-intercept. So x equals to 0, that means y equals to 2 times 0 divided by 0 minus 1, and which is simply 0. So 0 is the y-intercept. Okay, to decide the x-intercepts, we set y equals to 0. So this means this fraction has to be equals to 0. So solving this equation, we will again get x equals to 0. So this tells me that x-intercept and y-intercept are both 0. Right, so this is the step B. To investigate symmetry, let's start by substituting x by minus x. So this is what I will obtain. Simplifying this guy and notice that minus x squared is precisely going to be x squared. So what I'm getting at is precisely my original function. So this is telling me that the function over here is an even function. So to sketch the curve, all we need to do is to focus on the case when x is positive. So this is the information we have obtained in the previous slide. Now let's investigate the asymptotes. So let's look at the vertical asymptotes first. Since you see that the denominator equals to 0 when x equals to 1 and when x is minus 1, so it is necessary for us to compute the right-hand limit and the left-hand limit of the function at the point 1. Okay, as x approaches 1 from the right, x squared is a little bit greater than 1. So the denominator is a little bit greater than 0, while the numerator is positive. So this tells me that the limit is positive infinity. On the other hand, if x is approaching 1 from the left, you know that x squared is a little bit smaller than 1. So the denominator is a little bit smaller than 0. Meanwhile, the numerator is still positive. So this will tell me that my limit is minus infinity. This tells me that x equals to 1 is a vertical asymptote. Since the function is even, we all know that x equals to minus 1 is also a vertical asymptote. Now let's determine the horizontal asymptote by looking at the limit at infinity. That means we need to divide everything by x squared. So, well, dividing 2x squared by x squared, this is what I will get. And dividing the denominator by x squared, well, the first term gives me 1, and the second term gives me 1 divided by x squared. Okay, so this limit is easy to compute. Well, this guy simply approaches 0, so what I will get is simply 2. So this will tell me that the horizontal asymptote is y equals to 2. And moreover, since the function is even, we see that the limit of the function when x approaches minus infinity, well, this limit is also going to be 2. Okay, so these are the asymptotes we have found. We have vertical asymptote, x equals minus 1 and x equals 1, and we have the horizontal asymptote, y equals to 2. To analyze E, F, and G, we will need to find y prime and y double prime. Okay, so here's how we find y prime. We first use the quotient rule. Well, square the denominator, then denominator with numerator prime minus numerator with denominator prime. So the derivative of 2x squared equals to 4x, and derivative of x squared minus 1 equals to 2x. So if you multiply out the first parenthesis, you will see that the first term is 4x times x squared, which is 4x cubed. And this guy, 2x squared times 2x is also 4x cubed. So this 4x cubed and this 4x cubed will cancel out. What remains is simply minus 1 times 4x. So I will put this minus 1 in the front. So this will give me y prime equals to minus 4x divided by x squared minus 1 squared. All right, so this is my y prime. To get my y double prime, I will need to use the quotient rule again. Square the denominator, then denominator with numerator prime minus numerator with denominator prime. Okay, so the first derivative is quite simple. It's simply 4. The second derivative, on the other hand, requires the chain rule. So you use the chain rule, you view the square function as the outer function. The derivative of outer function is simply 2 evaluated at the inner function. So it's going to be 2 times the inner function times the derivative of inner function, which is x squared minus 1. Well, the derivative of x squared minus 1 is simply 2x. So this is obtained by the chain rule. Okay, to simplify this guy, we will first notice that the numerator has a common factor x squared minus 1. So we can get rid of this guy and this square, and moreover, rewrite this guy to be cubed. So this way we cancel out the common factor. So what's left in the numerator? So we have got 4 times 1 copy of x squared minus 1. So this is how this term comes from, together with 4x times 2 times 2x. Well, these guys will combine to be minus 16x squared. Okay, multiply everything out. So I will get 4x squared minus 4 minus 16x squared. Well, this 4x squared minus 16x squared will simplify to minus 12x squared, while this minus 1 times 4 will give me minus 4. Okay, so now we will just use the minus sign in the front to get rid of this negative signs. So what remains is 4 plus 12x squared divided by x squared minus 1 to the cube. Okay, so this is my second derivative. So these are the derivatives we have obtained in the previous slide. Analyze them a little bit, you will see the following. So if we set y prime equals to 0, we see that x equals to 0. And if we consider the points where y prime does not exist, we will find that x equals to plus minus 1. Okay, so if you are asked to find the critical numbers, then x equals to 0 is the only critical number because minus 1 and positive 1, they are not sitting in the domain. Okay, so we can also find from the expression of y double prime that y double prime is nowhere 0. And moreover, y double prime does not exist. when x equals to plus minus 1. So even though plus minus 1 are not regarded as critical numbers of the function or the derivative of the function, we will still keep them on the number line because we need to understand what happens near them. Okay, let's try to determine the intervals for increase or decrease. And since x equals to 0, x equals to plus minus 1 are the points where y prime gets strange, so we will still keep these vertical line segments here, though these two guys are not really the critical number. Okay, so then let's try to determine the sign of the derivative y prime over each interval. So when x is greater than 1, you see that the denominator is positive while the numerator is positive. But then together with the minus sign in the front, we see that the y prime is less than 0. So for the increasing test, the function is decreasing. Similarly, when x is between 0 and 1, so the denominator is still positive, the numerator is still positive. So over here with a negative sign over here, we see that the function is decreasing. Okay, so between minus 1 and 0, so the denominator is positive while the numerator now becomes negative. So together with negative sign in the front, we see that y prime is positive. So the function is increasing. Okay, so similarly, when x is less than minus 1, so the same situation applies here, so that the function is still going to be increasing in this interval. Okay, so to find the local maximum and minimum, so notice that 0 is the unique critical number in the domain. And from the first derivative test for over here, you will see that the function value at the point 0 is the local maximum. And if you plug in x equals to 0 into the expression over here, you will see that the function value takes 0. So 0, 0 is the point where the function takes the local maximum. All right, so this finishes the step F. Now let's look into concavity. So from this analysis, we know that x equals to plus or minus 1 will possibly be the point where the concavity changes. So let's simply consider these two vertical line segments. So then we have to discuss the concavity over these three intervals. So when x is greater than 1, well, the denominator is positive and the numerator is always positive. So in that case, y double prime is positive. So that way we know that the function is concave upward when x is greater than 1. Okay, so when x is between minus 1 and 1, you see that the denominator is actually negative. Well, the most convenient way to test this is simply to plug in x equals to 0. So you get minus 1 to the cube, which is negative. All right, so we know that the denominator is negative on this interval while the numerator is always positive. So that way I know the function is concave downward because this fraction is negative. Finally, when x is less than minus 1, you will see that the denominator is going to be positive. So then with the positive numerator, we will see that the function is going to be concave upward because y double prime is positive. Okay, so this is the analysis of concavity. And notice that minus 1 and 1, they are not in the domain, so they are not the inflection points. Let's also understand what's going on with these 2 points. So at the point 1 and at the point minus 1, we know that they give vertical asymptotes. And we also know from the previous slides that the left-hand limit at the point 1 of the function is precisely minus infinity, and the right-hand limit is positive infinity. And similarly, at the point minus 1, we know that the left-hand limit is positive infinity, and the right-hand limit is minus infinity. Okay, so also with the horizontal asymptote y equals to 2, we have determined from here, we can draw the diagram in the following way. So first, we have got the asymptotes y equals to 2, and x equals to 1, and x equals to minus 1. All right. And also we know that the function is approaching positive infinity when x approaches 1 from the right. So that's how we see this part. And the function is approaching minus infinity when x approaches 1 from the left. That's how we see this part. Okay, to determine how this curve is approaching the horizontal asymptote, we need to use the information we have obtained from here that the function is decreasing. So the function is getting close to 2. Meanwhile, the function is decreasing. So the only possible way is to approaching 2 from above. It's impossible for the function to approach 2 from below or in an oscillation way because all those ways of approaching y equals to 2 will contradict our analysis that the function is decreasing over here. So this is how we obtain this part of the graph. Okay, so this is what happens when x is positive. We also know that the function takes the value 0 at the point 0. Then, since the function is an even function, so what happens when x is less than 0 is precisely reflected from what happens to the right about the y-axis. So this is how we figure out this part of the curve and this part of the curve and this part of the curve. Okay, so this is our preliminary sketch. What remains is simply to connect these bits of the curve. And there's the only way that is consistent to our analysis is simply this way. So the function will decrease from positive infinity to 2, well, in the way that is concave upward. And moreover, the function will be decreasing from 0 to minus infinity, well, in the way that is concave downward. All right, so then the other part is simply obtained by symmetry. That's basically how we finish example 1.